Okay. So 4.3 is talking about the concavity of a function, and then points of inflections. And in order to figure out concavity and points of inflection, we are going to use the second derivative test. Okay. So, so far we have learned, at least in this section, that a first derivative analyzes the slope. And in using that, we can then find critical values, which helps us to find max and mins. Okay, the second derivative is going to help us with the curvature of the function. Okay, they call that concavity. Okay, so have you guys heard concavity before?
I didn't hear that yet.
Like in maybe science class when they talk about
How many calculus last year?
or yep.
That'll get you.
Yep. Or they talk about it with light. No, they don't teach. Okay. Anyway, the best way to kind of think of concavity is like a smiley face. Okay, so if you have a concave up scenario, you can draw a happy face. See how that kind of makes a happy face? That's a concave up. Okay, and concave up occurs when our second derivative is greater than 0. Okay, so we have like a cup effect. Concave downward, or a sad face, occurs when our second derivative is negative. Okay, so yep, there's your little smiley face analysis. Okay, and then a point of inflection. Does anybody remember when a point of inflection occurs? Okay, so when you go from concave up to concave down. So that is a point of inflection, or vice versa. That's hard to do. Okay, so the graph has a tangent line at that point. Okay, so there's two pieces of information that help us to identify points of inflection. The first is that the tangent line, or the graph has a tangent line at that point. So what does that mean? How are we going to find if the graph has a tangent line at that point? Close. The slope is equal to 0. Okay, so you're going to have that, or it's a vertical tangent line. Okay, so points of inflection do happen at critical values. Okay, and our concavity does change, so from a positive to a negative. Okay, so the basic function that you can kind of think of having a point of inflection is a John Travolta. Okay, so that point where kind of the neck would land is going from a negative concavity. So this right here is the sad face, but it's just half of the sad face. Okay, and then over here on the right side goes to a happy face. Okay, what is the value of the slope right at that spot? 0. Okay, so it's possible you'll get a potential like, oh, this could be a max or a min here, but when we do our second derivative test, we find out that in fact it's not a max or a min, it's a point of inflection. Okay. Okay, so they start by drawing us a picture so we can graphically kind of understand this idea. So question 1 says, on which intervals is the graph concave up? Okay, so we're using x values to identify our intervals. So between x values, do we have a happy face effect? Okay, so we go from -2 to -1. Okay, so -2 to -1. So I'm just going kind of left to right. That's a happy face. Okay, and then the next interval is sad face. Right? Okay, then -1 to 1 is a sad face, so that's a concave down. So we can put -1 to 1 down here, right? What were you saying, Faith?
Do you include the values as a bracket?
No, you do not include the brackets because, again, just kind of like the point of a max or a min, that's going to be where your concavity is 0. So at those specific points, there is no concavity. Yes.
I got a question.
Yes.
On like 3 to 5, like that's starting to like a nice curve. So is that the same thing? Is that kind of like
From 3 to 5. Okay, so yeah, you're right. 3 to 5 looks very straight and very linear.
yeah, but one's
Right.
straight and one's like curved this way, like not curved this way.
Okay, so I kind of think that from 3 to 4, that it is a straight line. Okay, so from 3 to 4, that is no concavity. A straight line is not curved, but I think from 4 to 5, that's going to be a happy face.
I agree. All right.
Okay, so what about from 1 to 3? 1 to 3, what would that concavity be? That's a happy face, so that's concave up from 1 to 3. Okay, we just talked about from 3 to 4 being straight, being linear, so it has no concavity. 4 to 5 is a concave up. Okay, and then what about my last little curvature from 5 to 6? Concave down. 5 to 6.
I'm leaving my stuff. Which means I'll be back.
Okay.
I don't want to go.
So question 3 says, at what intervals is there no concavity? Okay, so from 3 to 4, that little stretch where we had a straight line.
Can I have Steve and Jesse to the office to check out, please?
Sure.
Thank you.
You're gonna check out. Email me. What the heck? This is my way home.
Okay, so where do you see points of inflection?
Wait, isn't there a concavity from 6 to 7?
Wait, what?
6 to 7.
Oh, I didn't even see 6 to 7. Good eye. 6 to 7, I totally agree with you. I didn't even notice that was part of the graph. I thought it ended at 6.
And then 5, 1.
Okay, so our points of inflection are at 5, 1. I would agree with that. Yep.
Oh, and 1.
And yeah, and 1, 1. Do you guys see any other points of inflection? Huh? Okay, so let's talk about this point. This one right here. Okay, so I agree with you that it goes from a happy face to a sad face. So we go from a negative or positive to a negative concavity. But what is the other piece that must be true? It must have a tangent line. So what does that mean? Okay, it has to have like a slope of 0 or a slope of something. Okay, so it can't be a sharp point.
Get out of there.
Okay, so that point is not going to work because it is a sharp point.
So is the change in concavity only from like positive to negative, or can it be from positive to negative?
It can be from positive to negative or negative to positive. Yes, both ways. Because like an example would be if I took a John Travolta and just made it negative. Flip it the other way, then it's going from positive to negative.
So like 4 to 4.
What's that? Right, 4-2 would be the same situation. 4-2 is not going to work. We have a sharp point, right? So it can't be a point of inflection. Good? Okay. So analytically, okay, which means without looking at a graph, we can find concavity intervals and points of inflection by using the second derivative number line. Okay, so just like we did a number line for our increasing and decreasing slopes, we're going to do the same thing with concavity. Okay, when you start doing multiple number lines, I think that it is smart to start labeling your number lines. Okay, this number line is referencing our first derivative. Okay, so you should put like what you're doing next to it. Okay, obviously we're going to be doing second derivative ones for this one. Okay, so the procedure is parallel to the procedure used in the last lesson to find increasing and decreasing intervals and relative extrema by using the first derivative number line. Okay, so all we're going to do is we are going to take our function, we're going to find its second derivative. Okay, we're going to then set it equal to 0 to find our critical values, and then we're going to do a number line test and see if we have any positive to negative or negative to positive. Okay. All right, here we go. So first derivative. What is my first derivative of question number 5? Four x cubed plus 3x squared minus 6x. Okay. And now if I take a second derivative, my second derivative is good. Minus 6. Okay. So now once I have my second derivative, what is the next thing that I do? Set it equal to 0 and solve. Good. Let's see. So for this one, we have a couple of options here. You could start by dividing by 6 to make it smaller right off the bat. This one is going to be factorable, by the way. So you guys want to divide by 6 first?
Yes.
So then we get 2x squared plus x minus 1. So this is factorable. It is fair game if this was a calculator portion to just throw this into the calculator and find when it's set equal to 0. Just so you know, this factors into x squared minus 1 and x plus 1. Oh, I said 2. Yeah, I meant to say 2x. Excuse me. I wrote it correctly and said it incorrectly. My bad. Okay, so my critical values are where? Negative 1/2 and negative 1. Or positive 1/2. Excuse me. What am I thinking? Thank you. Doing the easy stuff wrong. That's not good. Alright, so I'm going to do my number line test. So I'm going to write next to this that this is a second derivative number line test. Okay? The next section, you guys, is going to be over graphing things. So you will be using both number line tests. So start by getting into the habit of drawing which number line test you're using now before we start doing the more complex things. Okay? Alright, so remember, second derivative here. So if I plug a value in that is less than negative 1, such as negative 2, into my second derivative, will I get a positive or a negative value? Yeah, definitely positive. Good. Okay, if I plug a value between negative 1 and 1/2 in, I get a... Yep, like such as 0, you get a negative, and if I plug a positive value bigger than 1/2 in, you get a positive. Okay, so right here, I can tell you that we have 2 points of inflection. Okay, we have 2 values where you're going from a positive to a negative, and then a negative to a positive. Okay, so just so you know, this function is concave up between which values? Okay, so from negative infinity to negative 1, and from 1/2 to infinity. So therefore is concave down between negative 1 and 1/2. Okay, so we're listing our intervals just like we did when we were working with increasing and decreasing values. Okay, and now we're going to find our points of inflection. I'm going to call it PI for point of inflection. I'm not throwing in an O. I don't know why. So where is my point of inflection? So the first one is at negative 1. So for me to say a point, I need a y value. How do I find the y value? Plug it into the original. So if I go back to the original, I would get, let's see, negative 4 plus 3, which is negative 1, and then plus 6.
Going back to the original?
Yes. Oh, I'm not going back to the original. I mean, back to the other original, not the first derivative. I can't see that far. Okay, let's try again. So if I plug -1 into the original, we would have 1 minus 1, which is 0, minus 3, which is -3, plus 1. Does anybody agree with -2?
Sure.
Okay, if I plug 1/2 in, can I go ahead and tell you what you get when you plug this in a calculator? I'll let you know that this actually simplifies to 7/16 when you throw that into a calculator. Okay, everybody okay with all of that so far?
Yep.
Pretty good?
Yes.
Excellent. All right, so question number 6, we have a slightly more exciting function. Okay, it happens to be rational, and anytime you're working with rational functions, the very first thing you need to think about is domain restrictions. Okay, so first of all, where do I have domain restrictions? Okay, so domain x cannot equal plus or minus 2. Okay, so remember that when I do my number line test, that those are critical values as well. Okay, what's happening on this particular function at 2 and -2? A vertical asymptote. Okay, so try to visualize what this is going to potentially look like. We have 2 vertical asymptotes. We probably are going to have slides on the side. Okay, there could be a potential John Travolta in the middle or something parabolic. Okay, yeah. All right, so they were super awesome and gave us the second derivative. So immediately what we're going to do is we're going to take that second derivative and set it equal to 0. Okay, so we're going to take that, set it equal to 0. We want to start by filling in values that make the function undefined. Okay, so making the denominator equal to 0, we have critical values from that. Okay, so those are going to be the same critical values that we got from our domain restrictions before. Okay, it's possible they could be different, so always double check them. They are the same. So the bottom makes the same critical values as our domain restrictions. If I set the top equal to 0, what do I get? So the 10 goes away. Yeah. We get plus or minus, the square root of 4/3. Isn't that 2 over the square root of 3?
Yeah.
Yeah.
Plus you. Plus you.
Wait. Yeah. That's what I was just looking at. I was like, wait a second. Because your first step is that you subtract 4, and then you divide by 3 and take the square root of negative. So right here, you end up with no critical values because the value from solving this is imaginary. None. Okay, so we are only going to have the 2 critical values that exist on our number line from our domain restrictions. Okay, so remember this is a second derivative test. So if I plug a value that is less than -2 into my second derivative, such as -3, so plugging -3 in, I'm going to get a positive on the top, right? And on the bottom, if I plug in, that would also be a positive. So I get a positive over a positive. Okay, a value between -2 and 2. 0 sounds pretty great. So if I plug 0 in, I get a positive on the top, but I get a negative on the bottom. Okay. For question number, or for interval number 3, if we plug 3 in, we're going to get a positive. Okay, so tell me what I have. So we have a concave up between which intervals? -∞ to -2. And 2 to infinity. Concave down between -2, and 2. Point of inflection. Do we have points of inflection at -2 and 2?
Right. Right.
Yeah, we do?
Yes.
Because remember what initially was happening?
So there's vertical asymptote.
Yeah, it's a vertical asymptote. So can you find a tangent line at a vertical asymptote? No. Okay, so there are no points of inflection for this. Points of inflection.
You're fat.
So I kind of think this is pretty interesting. I can tell you exactly what this function looks like just based on the concavity of it. So we know, just from all of our experience with working with rational functions, right, we have a vertical asymptote at 2 and one at -2. Okay, without me finding like actual values, I know that we always have slides on the two ends, right? Okay, this particular one would have a horizontal asymptote at 1, if you remember our is it bigger on top, is it bigger on bottom situation. So I have slides there. Just based on the concavity, if I have a happy face on my left one, which of the sides of my happy face have a, wait, what am I trying to say? Are going to fit into that slide. So like if I was, it's either going to be this slide or this slide. So which of those two slides is a happy face?
The top one.
The top one, right? Okay, so kind of the same situation on my other one. It's either going to be that slide or that slide. Which one is the happy face? The top one. Okay, in the middle we have a sad face. It's going to look like a parabola, and I don't know exactly how high. We would have had to use the first derivative test. We would have found a critical value in the middle there. It might have hit exactly at 0, 0. It might be down 5 units. I don't know. We could have analyzed it, but it looks like that. Okay. So the second derivative test. We've basically been using this idea, but now we're going to kind of go just a wee bit further and say that not only can we use second derivative tests to figure out concavity, but it also helps us define max and min values. Okay, so if I know where my critical values are on my first derivative, I can use that information on a second derivative to decide if it's a max or a min, just based on the concavity. Okay, so like for example, if I know I have a critical value at this point and I have a happy face, then I know that that spot is going to be a minimum, right? If I know that I have a critical value in the middle of this sad face, it's going to be a maximum. Okay, so it's another way to find a max or a minimum. Okay, so this little note says the second derivative test does not always give an answer, okay, when your first derivative is or second derivative is equal to 0. Use it only when the directions require it or when the given information requires it. Okay, so basically what that is saying is if they ask you to find a min or a max, you can still use that test that we did last section. Okay, you can use a first derivative test with the number line to find a max or a min, but if it specifically says use a second derivative to do it, then you have to use the concavity to make your statement. Okay, so question number 7 is find the max or the min of this particular function. Okay, so what am I going to do first in order to find potential maxes or mins? Derive it, right? So first thing I'm going to do is I'm going to find the first derivative, and the first derivative is where I find potential maxes or mins. So first derivative is negative 12x cubed plus 12x. Okay, so then I'm going to take that and I'm going to set it equal to 0 to find my critical values. Yep, I'm going to get to that after I find my critical values. Okay, so I can factor this. If I pull out a negative 12x, what's left over? x squared minus 1. Okay, so x squared minus 1, so I end up with critical numbers at 0 and plus or minus 1. Okay, so instead of doing a number line test on the first derivative right now, I'm going to stop, and I'm going to keep going, and now I'm going to use the second derivative test to decide on the concavity of those. Okay, so second derivative, what is my second derivative? Negative 36x squared plus 12, good. Okay, so at this point, all I need to know is the concavity of those critical values. Okay, so I need to know whether the concavity is positive, is it a happy face, or is it a sad face? Okay, so I'm not actually going to set it equal to 0. I don't care about points of inflection. I'm just looking about, is it a concave up or concave down? Okay, so all I'm going to do is I'm going to take those critical values that I just found, and I'm going to plug them into my second derivative to figure out if my concavity is positive or negative. Okay, so if I plug 0 in, what do I get out? I get a 12. Okay, so all I care about is that this is a positive concavity. I got a positive 12. Okay, so a positive 12 tells me I have a happy face concavity. So what is happening at the value of 0? Is it a max or a min? It is a min. So we now know that 0 is a minimum point. Okay, we'll go ahead and find its corresponding y value here in a second. We'll keep going with our mins and maxes here. Okay, so now I'm going to do my second point. So let's just plug 1 in. So if I plug 1 in, negative 36 plus 12 is negative 24. So I got a negative, which is a sad face. Okay, so if it's a sad face, what is happening at the x value of 1? It's a max. So we have a max at the, whoa, not a man, that's different. A max at the x value of 1. Okay, and then our last critical value was negative 1. Okay, and if we plug negative 1, we get the same thing, don't we? So we get negative 24 again. So again, a negative concavity, so we know it's a max. Okay, so they do ask us to find the points, so we need their corresponding y values. So I need to go back to the original. So for 0, if I plug 0 in, what pops out for my y value? 0. For the x value of 1, that would be, let's see, negative 3 plus 6, I'd get 3. Okay, and then the last one would also be 3. Okay, so those right there are your mins and maxes. So a different way to find maxes and mins. Oh, I didn't write a negative, thanks. Minor detail. Okay, is that it? Are we done? Oh no, we got more. Oh, I love these questions.
I know.
They're like my favorite. Okay. So they're giving us this g of x function, and they give us first, like this first line here is all about first derivatives. So it says the first derivative at negative 3 is 0, first derivative at negative 1 is 0, first derivative of 0 is 0, and first derivative at 2 is 0. So what are the things that they're telling us right now? They're giving us critical numbers. Okay, so immediately I know that anytime my first derivative is set equal to 0, I have critical values at the x values of negative 3, negative 1, 0, and 2. Okay, so now I have to decide if these are going to be maxes or mins. Okay, so the second derivative test tells me the concavity. All I'm trying to figure out is if I have a positive concavity, is that going to be a min or a max? and negative and vice versa. Okay, so the second derivative at negative 3 says that it's a value of 4. So what does that information tell us? It's what? Okay, positive, so we get a happy face, right? So it's a min. So we have a min at x equals negative 3. Okay, then the second derivative of negative 1 gives us a negative 2. So that's a sad face, right? So what's happening at negative 1? Max. You guys paying attention back there? It looks like you got your own little world going on. Okay, what do you think's happening at 0? If they tell us that the second derivative is 0, what would that potentially be? It could not necessarily be vertical, but it could potentially be a point of inflection. Okay, where it goes from positive to negative, right? Okay, so we could have a point of inflection there, but it is definitely not a min or max, right? Okay, so that would be a potential like on a John Travolta where it's going like so. So 0 is not going to be either. Okay, what about the x value? If they give us this information right here, x value of 1 being a 5, what are they telling us there? It's concave up. So is that going to be a max or a min? Okay, so the only way for us to have a max or a min is for our first derivative to equal 0. Okay, and since it's not given in the information of our first derivative, basically this piece of information is completely irrelevant. Okay, it's just trying to throw us off. Okay, so there's no critical value in a first derivative where the x value is 1, so we can't say it's a max or a min. It does tell us it's a concave up, but unless we are trying to analyze points of inflection, that information is useless. Okay, what about at the x value of 2, we have a second derivative of positive 3. Okay, so we get a happy face, so what is happening at 2? It's a min. Whoa. Okay, so all the information that we can gather is that we have a min value at, or mins at x values of negative 3 and 2, and maxes at negative 1. That's all we can do, yeah. Yeah, that's all they're asking us to do. It just says find the relative maxes and mins. So. Okay, so that's it for you guys.